Good day. Today's topic is all about atomic orbitals and quantum numbers. So at the end of this lesson, you should be able to first describe the four quantum numbers and their significance and recognize orbital shapes based on the given quantum numbers. So, the quantum mechanical model of the atom is the model of the atom that describes the electrons inside the atom. So, and this set of quantum numbers acts like an address for each electron. Yes, there is still what we call a probability only that we can find these electrons in the atom. So, atomic orbital is the region around the nucleus with the greatest probability of finding electrons. So this is also called atomic sublevel, or simply as orbitals. So how do we describe the atomic orbital? We use these necessary four quantum numbers to describe the atomic orbital. First is principal quantum number. Second, azimuthal quantum number, also known as angular quantum number, magnetic quantum number, and the fourth one is spin or magnetic spin quantum number. So these are the four quantum numbers that is used to describe the atomic orbital and the electrons in the orbitals. So what does each of these orbital speaks about? How does each of these quantum numbers explains about the existence of electrons in the orbital? So when you say principal quantum number, it is represented by a small letter n, and it designates this number represents the size of electrons or of the atomic orbital from the nucleus. Second, the azimuthal quantum number is represented by L, which describes the shape of the orbital. And the third, magnetic quantum number, represented by m sub L, and this quantum number specifies the orientation or position of the orbital. And lastly, the spin quantum number or magnetic spin quantum number describes the spin of electrons. So we know that electrons move very fast around the atom. So spin quantum number specify how does it spin inside the atom. So according to Wolfgang Pauli, who established the Pauli exclusion principle, which states that no two electrons in an atom can have the same set of four quantum numbers. So that means that no two electrons can have the same four quantum numbers, even if that one orbital can hold two electrons. But even if two electrons can be found in one orbital, these two electrons would still have different spin quantum numbers. So when we say quantum numbers, we are actually stating the probability only. Okay, unlike Niels Bohr, that there is a fixed path and fixed location of electrons, but quantum numbers is used to state the probability of finding an electron in a certain location. So this probability can be shown graphically with an electron density diagram. So if you're going to look, for example, at this image below, where you will see more dots in some regions and fewer dots in some regions. So the regions where there is actually more dots, that shows a higher probability that you can find an electron there. On the other hand, regions there where there are few dots means low probability of finding an electron. So let's start with the first quantum number, called principal quantum number, represented by letter n. So when we say principal quantum number, it refers to the distance of the electron from the nucleus. It is known as the shell. It is also known as energy level or principal shell. And these n, we represent them with values. And the acceptable values for the principal quantum number are positive integers, such as 1, 2, 3, 4, and so on. And as the value of n increases, that means the distance of the electrons becomes farther from the nucleus. So again, principal quantum number is also called a shell or energy level. And this energy level contains orbitals with the same value of n. So again, the farther an electron is from the nucleus, the greater the numeric value for n. So for the known elements that we have in the periodic table, n is equal to 1 through 7. So if we're going to look at it, so you will see here 1, 2, 3, 4, 5, 6, 7. So these represents actually the principal quantum number. So that means this is energy level 1, 2, and 3, 4, 5, 6, and 7. Now, how we know that energy level would help us know that there is a probability that we can find an electron there. But the question is, how many electrons can we find in each energy level or in each shell? So to compute the maximum number of electrons in the principal quantum number, or in n, we use 2n squared. So for example, if the value of n is 1, then the maximum number of electrons is 2. Why? Because if we're going to substitute n with 1, that will be 1 times 1 times 2 is equal to 2. So the maximum number is 2. If the value of n is 2, so using this equation, that would be substituting n with 2, that would be 2 times 2 multiplied by itself times 2, we get 8. If the value of n is 3, so substitute n with 3, that will be 3 times 3 is equal to 9 times 2 is equal to 18. So very simple to know the maximum number of electrons in a shell or in the energy level. So we know that the n is a principal quantum number. So at the fourth energy level, there is a maximum of 32 electrons. For energy level 5, it can hold up to 50 electrons. Energy level number 7 can hold up to 72. And if the value of n is equal to 7, it can hold up to 98 electrons. So, again, when you say principal quantum number, it is denoted by a small letter n, and that n represents the principal shell or the energy level. And the value that n represents would always be a positive integer, where n is equal to 1 or 2 or 3 or 4 and so on. So when you discuss about electric configuration when you were in grade 8, so you usually do this, right? Using the mnemonic 8. But what does this number before the letters represents? So this number, 1, 2, 2, and 3, is the principal quantum number, or the main energy level, or the principal shell, or simply as the shell. So let's say, for example, sodium. So sodium is an element that we can find in the periodic table. So let's say this is the nucleus, and in the first energy level, so this is n is equal to 1, we can see here the small dots could represent the electrons. So there are actually two. There are actually 2 electrons, right? So that is why, because these electrons are found in the first energy level, so that is why it is 1s2. So the 2, the superscript here represents the number of electrons. Now in energy level 2, which is in the second orbital, so if we are going to count that, it will be 1, 2, 3, 4, 5, 6, 7, 8. So in the second energy level, there is a total of 8 electrons. Because these are found in the second energy level, that's why the principal quantum number is 2. 2s2, 2p6. So if you're going to add this, if you're going to add 6 and 2, that will be equivalent to 8. So that is equivalent to the total number of electrons in the second energy level. And on the third energy level, which is the outermost shell or energy level in sodium, has only 1 electron. That is why we use number 3, because the electron is found at energy level 3, with a superscript of 1, because 1, there is only 1 electrons. So that is now the reason why we use this whole number before putting the letters in the superscript. So this number represents the principal quantum number, or the principal shell, or the energy level. Now you might be asking me right now, what does this SP stands for? So we will find that out later on as we progresses in our discussion. So now let's go to the second quantum number. It's called the azimuthal quantum number. It is also called angular momentum quantum number. So when you say azimuthal quantum number, it is represented by L. And this quantum number, we use this to describe the shape of the atomic orbital. If the principal quantum number, we call that as the main energy level. Azimuthal quantum number, we call that as sub-level. Or principal quantum number is called shell, so azimuthal quantum number is also known as sub-shell. Okay, do not be confused with that. So what are the allowed values for azimuthal quantum number? So the allowed values for L are 0 to n minus 1. Again, n is the energy level, or the principal quantum number. So whatever the principal quantum number, we're going to minus it by 1. So that's how we get the values for azimuthal quantum number. And that each value of azimuthal quantum number corresponds to a sub-shell shape. So there could be more than one allowed values, okay, for this azimuthal quantum number, and that each value would correspond to a particular shape of the subshell or of the sub-level. So again, L describes the electron energy sublevel or subshell. So how do we know, how do we identify how many sublevel are there in every energy level? So very simple. Each electron energy level n has n sublevels. So that means whatever the number of the energy level will also be the number of sublevels. So if it's energy level 1, then how many sublevel it has? Can you guess? Okay, so the answer is 1. Energy level 2 has how many sublevels? Very good, it's 2. Energy level 3 has how many sublevels or subshell? Right, 3. And energy level 4 has a total of precisely 4 sublevels. If it's energy level 5, it would have 5 sublevels, and energy level 6 would be equal to 6 sublevels. And let's say if there is energy level 7, then it would have 7 sublevels. So now you know how many sublevels or subshells are there in every principal shell or main energy level. Now, these sublevels in the known elements in the periodic table, we represent them by letters. So now, the letters that we usually use when we do the electron configuration, these are S, P, D, and F. So S, P, D, and F are the letters that we use to represent the sublevels. So S sublevel, P sublevel, D sublevel, and F sublevel. So, but these letters corresponds to a value, right? Because we said earlier that L is equal to 0. From 0, it can range from 0 to n minus 1. So the orbital designation for S, the value is 0. For P, it's 1. For D, it's 2. And for F, it's 3. Okay, so that means if the value of L is 3, that means it's in the F orbital. If the value of L is 2, that means it's under D orbital. If the value of L is 1, then it's in P orbital. And if the value of L is 0, that means it's S orbital. Did you get it? Okay, great. Now this collection of orbitals with the same value of n and L is what we refer to as subshell, or again, sublevel. So in the periodic table, we can actually also identify here which one is S block, P block, D block, and F block. So this is S block, this is P block, this is D block, and this is F block. Okay, now let's go, because we said that it describes the shape. Azimuthal describes the shape of the orbital. So now let's start with orbital S. So why is it called S? Because S for sharp. So the atomic orbital S has a spherical cloud. Okay, so the shape of that orbital is spherical in shape. So it looks like that. So 1s, 2s, 3s, whatever the corresponding energy level it is found, so it has the same shape wherever energy level it is. So it is always spherical in shape, the S orbital. While the P orbital, Okay, why P? Because P for principle. It is the shape of it is dumbbell shaped cloud, having two lobes on opposite sides of the nucleus. So this orbital has three types based on their orientation. It's px, py, and pz. Px means its orientation is along the x-axis, py, the orientation is along the y-axis, and z is along the z-axis. So here, so it looks like a dumbbell shape, right? Having these opposite lobes towards each other. So this is px, py, and pz. So this one is the p sublevel, okay, or the p orbital. So the d orbital now is represents for diffused, okay, d for diffused. And what's the shape of the orbital? It's a four-leaf clover, as an hour and as a ring. So the orientation, it is actually 5 orientation or spatial orientation, which is dxy, dx squared y squared, dxc, dz squared, dyz. So that's how it looks like now. So this is the d orbital, okay? D orbital. Why 5? Because it has 5 orientation, or it has, that means this is one orbital, one orbital, one orbital, one orbital, and another one orbital. It's a total of 5, right? 5 orbitals under d orbitals. Now for f orbital, f for fundamental, there's no definite shape for this because it's too complex to visualize them. There are 7 orbitals, f orbital, which have complex appearances. So here there are 5 d orbitals having different spatial orientation, while the p orbitals have 3, right? So 3. S has 1. So this is how it looks like, the model of f orbital. So okay, so if you're going to count, it's 1, 2, 3, 4, 5, 6, 7. So there are 7 orbitals under f. So now, so to better understand azimuthal, okay, if the value of L is 0, so we know that 0, the symbol for that is the S. And we know that if it's S orbital, the shape is always spherical. If the value of L is 1, we know that 1, its symbol is P, and the shape are all dumbbells. Okay, and if the value of L is 2, then the symbol for 2 is d orbital, which has 1 dumbbell and the rest are clover leaf. And if the value of L is 3, then its symbol is F, which is too abstract to describe. So in summary, for the azimuthal, it's denoted by L, so that L represents the subshell or the orbital or the sublevel, wherein the allowed values can be from 0 to n minus 1. Okay, so for example, if n is equal to 1, therefore the value of L is 0. Why? Because 1 minus 1 is 0. So the value of L is 0. And we know that 0 is an s orbital. The symbol is s. Now, if the value of n is 2, so what is its corresponding L value? So the L value would be 0 or 1. Why? Because 2 minus, using this 1 and minus 1, 2 minus 1 is equal to 1. So that means the allowed values for the allowed azimuthal values for energy level 2 is 0 and 1. So we always include 0. If the energy, if n is equal to 3, so what is the allowed values for L? So that would be 3 minus 2. 3 minus 1, I mean. So 3 minus 1 is equal to 2. So therefore, the allowed values for azimuthal is 0, 1, and 2. If the energy level is 4, so what is the values for L? So 4n, which is 4, minus 1 is equal to 3. So what are the allowed values? It could be 0, it could be 1, it could be 2, or it could be 3. So we know if it's 0, if the value of L is 0, its symbol is S. If it's 1, then it's P. If it's 2, it's D. And if it's 3, the symbol is F. So now you know what do we mean by these symbols. So these symbols are the symbol that it represents for the azimuthal quantum number. And we know that these symbols has a particular shape, okay, that describes the shape of the orbital. So that is why here it will be 1s. Why 1? Because 1 is a principal quantum number, right? So 1s. How about this one? 2s and 2p. Why? Because the principal quantum number is 2. So that will be 2s, 2p. So this is 2s, 2p. If the n is equal to 3, that will be 3s, 3p, 3d. Because 0 is s, 1 is p, 2 is d. Okay? So if the n is 4, that means, so 0, 1, 2, 3 are the allowed values for L. And we know that 0 is represented by an S, right? So that's 4S. 1, P, 2, D, 3, F. Okay, so that is now for the azimuthal quantum number. Now let's go to the third quantum number called magnetic quantum number, represented by m sub L. So what do you mean by magnetic quantum number? Okay, again, it says earlier that it's all about the position or the orientation of the orbital. So the number of orbitals in a subshell is given by the magnetic quantum number, m sub L. So what are the allowed values for m sub L? It says it ranges from negative L to positive L. So we know that L is the azimuthal quantum number. So we substitute L here with the L value from the azimuthal quantum number. That would include 0. Take note, huh? The values of m sub L are negative L to positive L, including 0. Now, how many electrons can each orbital hold? The answer to that is 2 electrons. So don't forget, each orbital can hold of up to 2 electrons only. And orbitals with the same energy level are called degenerate orbitals. Now, so S sublevel has how many orbitals? It has only 1. P sublevel has 3 orbitals. D sublevel has 5 orbitals. F sublevel has 7 orbitals. Okay, so take note of that. And we know that each orbital can hold of up to 2 electrons only. So because S sublevel has 1 orbital only, that means how many electrons? Okay, it's 2 electrons. So P sublevel, how many electrons in total under P sublevel? Maximum number of electrons. Per orbital, it holds only 2. So that would be correct. It's 6, 5, 10, correct? And F, 7 orbitals. So each orbital can hold only 2 electrons. So it's a total of, yes, you got it right, 14 electrons. So pairs of squares on the periodic table are actually orbitals. So I know that you are very familiar with the periodic table. We know, so, and each box represents an element in the periodic table. But actually, we can also use that as a representation for orbitals. So each pair of squares, so two boxes here, represents one orbital. Okay, again, in the periodic table, if you wanna use the periodic table as your basis for the orbitals, so two boxes, or this pair of squares represents one orbital. So therefore this one is S block, one orbital. We know that this one is actually here on the other side, right? But we just put it here for the sake of for a better picture of a pair of square that represents one orbital. P block, as we said, has three orbitals, right? It's one pair, second pair, and third pair. So that's 1, 2, 3 orbitals. We know that one orbital can hold how many electrons? 2. So therefore 1, 2, 1, 2, 1, 2. That's a total of how many? Correct. 6 electrons. 1, 2, 3, 4, 5, 6. Well, in the D block, it has actually how many orbitals? 5. So it's 1, 2, 3, 4, 5. How many electrons in total? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. While F orbital has 7 orbitals and a total of 14 electrons. A maximum of 14 electrons that F orbital can hold. F sublevel can hold, I mean. So do not forget that each orbital can hold a maximum of 2 electrons. So in summary, M sub L, it's a magnetic quantum number. If the value of L is 0, that means what's the possible value of M sub L? So basically it's 0, right? But if the value of L is 1, then what would be the value of M sub L? The possible values for M sub L. So we know that, again, it's from negative L to positive L. So that would be negative 1, 0, positive 1. If the value of L is 2, that would be from negative L to positive L. So that would be negative 2, negative 1, 0, positive 1, positive 2. But if the value of L is 3, the possible allowed values for the M sub L would be negative 3, negative 2, negative 1, 0, positive 1, positive 2, and positive 3. So we know that 0, what symbol that it represents? The orbital designation symbol? S, correct. 1 is actually P, correct. 2 is T, and 3 is F. So if the possible value of M sub L is 0, then how many orbitals? It's only 1, right? So the maximum number of electrons would be only 2. Here, because 1 is P orbital, right? It's P sublevel. So how many orbitals? It's actually 3. So this is 1 orbital, 1 orbital, 1 orbital. So there's a total of 3 orbitals. So that means each orbital has an assigned value. Okay? So that means if there are 2 electrons here, it's negative. If the value of M sub L is negative 1, right? If it's in the second orbital, it would be 0. If it's in the third orbital, it could have a value of positive 1. Because it has 3 orbitals, then the maximum of electrons is 6. Well, here will be 5 because it's 1, 2, 3, 4, 5. Okay, how many total of electrons? 10. For here, it's actually 7. If you're going to count 1, 2, 3, 4, 5, 6, 7. 7 orbitals that can hold a maximum of 14 electrons. Okay. So here, you're going to see that if in the p orbitals, it's actually -1, 0, +1. So this will be the 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 orientation or the position of the atomic orbital where you can find the electrons. So that means one orbital is represented by a magnetic quantum number value. It could either, for a 3p orbital, it could be the m sub L could be -1, 0, or +1. So either of these three orbitals, there is a probability that you can find an electron here. So if it's 5d orbitals, so we know that d is represented by 2, right? So what would be the m sub L? That would be -2, -1, 0, +1, and +2. That's why it has 5 orbitals. Well, F, we know that F is the value of L for F is 3. So what would be the m sub L? So from -L to +L. So the allowed values there would be -3, -2, -1, 0, it's always included, +1, +2, and +3. So if you're going to count, this is one orbital, so 2, 3, 4, 5, 6, 7. So there are 7 orbitals under F sublevel. So in summary, when we say magnetic quantum number, it is denoted by the symbol m sub L. So what do you mean by magnetic quantum number? It describes the orientation in space of the atomic orbital. What are the possible values? It will be from -L, including 0, to +L. So how will you know as to how many, the total number of orientation? So for example, it will be 2 times the value of L plus 1. So we know is that L, that whenever it's equal to 0, it's s orbital. How many orientation? 1. So this one, the spherical shape, that's always s, right? So that means how many orientation? 1. If the value of L is 1, so how many orientation? That would be 3. Why? Because 2 times 1 is 2 plus 1 is equal to 3. So we know that this is usually the orbital designation of 1 is actually p. So how many orientation? 3. So this one, 1, 2, 3 orientation. So that's how it looks like, the orientation. And if it's 2, if the value of L is 2, so what's the total orientation? 5. So D, 1, 2, 3, 4, 5. So it's 5 orientation, which is dxy, dxz, dyz, dx squared y squared dz squared. So that is the orientation or the position of the atomic orbital. Now let's go to the last for quantum number that we can use to describe the electrons in the atom. It is the electron spin quantum number, or simply as the spin quantum number or magnetic spin quantum number. So spin quantum number is represented by the symbol m sub s. So when you say spin quantum number, as the term suggests, it describes the spin of the electron. So to what direction it moves as it revolves around the nucleus. So what are the possible values? So the possible values for the spin quantum number are only 2. It's either -1/2 or +1/2. So an electron that has a value of +1/2, that means it will spin in one direction, while an electron that has a value of -1/2 will spin in the opposite direction. So again, S, so the symbol for for spin quantum number is m sub s. Okay, in some books it's just s, so either of those two, but for this case let's follow the m sub s. So it describes the spin. So electrons can only have in the same orbital. Again, in one orbital one orbital can hold 2 electrons only. So if one orbital can hold 2 electrons only, then no 2 electrons would have the same spin. They would always have an opposite spin. So 1/2, if the value of m sub s is 1/2, that means the possible spin of the electron is in a clockwise direction. But if the value of m sub s of the electron is -1/2, that means it could possibly move in a counterclockwise direction or anti-clockwise. So here, so we know that the spin is a fundamental property of electrons, like its mass and charge. So spin up, +1/2. Spin down would be -1/2. So in summary, for spin quantum number, it is denoted by the symbol m sub s. M sub s meaning it's the spin of the electron, wherein the allowed values are only +1/2 or -1/2. So if the value of m sub s is +1/2, the movement of the electron is in a clockwise direction. And usually we use the symbol an arrow pointing upward. So that is the symbol. If we want to represent it through a symbol, it will be an arrow pointing upward. Sometimes it's half arrow or sometimes full arrow. Now, if the value of m sub s is -1/2, then the spin of the electron is counterclockwise or anti-clockwise. So if you want to represent it through a symbol, the arrow would be pointing downward. Okay. So that means from the 4 quantum numbers, or from the Pauli exclusion principle, no 2 electrons can have the same set of 4 quantum numbers, because no 2 electrons can have the same spin. Okay, the same spin quantum number or spin values. Okay, so there you go. We were able to discuss the 4 quantum numbers that are necessary to describe the orbitals. So we have the principal, angular, again this is azimuthal, magnetic, and spin. What are the symbol for principal? N, angular, L, magnetic, m sub L, spin, m sub s. What are the permitted values or the allowed values for principal? It's positive integers, 1 to 3 and so on. For angular momentum or azimuthal quantum number, the allowed values are integers from 0 to n-1. Magnetic, it's from -0, -L to 0 to +1. And spin can only have 2 allowed values. It could either be +1/2 or -1/2. So what does each quantum number explains about the orbitals? Principal, we're talking about the size. Angular, or the azimuthal, we're talking about the shape of the orbital. Magnetic, we're talking about the orientation. And spin is the direction of the electron spin. Okay, so there you go. So we're done with this. Energy level, principal quantum number, so number of electrons. For a specific type of subshells or sublevel with their corresponding number of electrons, energy level 1, the subshell would energy level 1 has how many sublevel or subshell? Only 1. So that's S. The number of electrons in the subshell is 2, and the number of electrons is also 2. So for energy level 2, what are the possible subshells or sublevel? It's actually S and p orbital. We know that S can hold how many electrons? 2. P can hold 6, so that means the total is 8. So why is it that energy level 3 can hold up to 18 electrons? Because energy level 3 has how many orbitals? 3 orbitals, right? It's S, P, D. So S can hold 2, P can hold 6, D can hold 10 electrons, a total of 18. Again, if the energy level is 4, what's the maximum number of electrons it can hold? It's 32. Why 32? Because we know that energy level 4 has how many sublevel? 4. Again, the number of sublevel would be equal to the value of its n. So because energy level is 4, therefore the subshell would also be 4. The total number of sublevels or subshells. So it's S, P, D, F, right? And S2, P6, D10, F14. So the total number of electrons in energy level 4 is 32. Okay, so again, the orbital designation S, the value for that is 0. P1, D2, F3. And we know that S can hold 2, P can hold 6, D can hold 10, and F can hold 14 electrons. So if the value of L is 0, the value of M sub L is 0, right? If the value of L is 1, that means the values of M sub L from negative L to 0 to positive L, so that would be, because the L value is 1, that would be negative 1, 0, positive 1. If it's 2, it's negative 2, negative 1, 0, positive 1, positive 2. And if the value of L is 3, that is negative 3, negative 2, negative 1, 0, 1, 2, 3. So we know whenever the value of L is 0, we know that it's the S. The orbital designation is S subshell. So number of subshell 1, right? When you say subshell, we're referring to this orbital, okay? Do not be confused. 1, we know that is P. So it has 3 orbitals, 2, 5 orbitals, that's D orbital, and 3, 7. Okay, so here we go. You can see here, N, whenever N is equal to 1, L would be equal to 0. And the value of M sub L would be 0. So each box represents orbital. One box represents one orbital. So that's why here you will observe that there's only one box, because this is one orbital, because we know that S has only one orbital. Same as here, Y2S because it's in energy level 2, right? Y1S because it's in energy level 1. So let's go here, 2P. So that is negative 1, 0, positive 1. So that means kung may electrons dito, if there are electrons here, so that means electrons can be found probably here in positive 1, 0, or negative 1. So this could be the allowed values of the electrons that we can use this to actually find the probability. And here 3s. Why 3s? Because 3, it's an energy level 3 or shell 3, and one box. Why? Because it's one orbital only. Here we have 3d. Why 3d? Because it's an energy level 3. Why d? Because the value of L is 2. Whenever the value of L is 2, that means it's in d orbital. So we know that d orbital has how many orbitals? It's actually 5. So it's negative, positive 2, positive 1, 0, negative 1, negative 2. You will observe here it starts with positive to negative, so that can be fine. Okay, let's go to an exercise. Okay, so let's start with this one example. Refer to this set of quantum numbers, which is 4, 4, negative 2, negative 1/2. Is this set of quantum numbers allowed or forbidden? So let's see. So step 1, if you want to know if the set of 4 quantum numbers is allowed or forbidden, so first is check the values of each quantum numbers and assess if they follow the rules. So we will start from the leftmost and check whether they follow the rules or not. So the first number, leftmost here, 4, this is the principal quantum number. The first number from the leftmost part is always the principal quantum number. So here it's 4. Now, we know that the principal quantum number allows integral values or positive integers. Therefore, if n is equal to 4, therefore it is an allowed value. So this is correct, 4. Next, check the values. Again, for the second value, it's 4. For the second value, it stands for the azimuthal quantum number. So we know that the allowed values for azimuthal are integers from 0 to n minus 1. So n is the energy level. So if the n is equal to 4 here, so therefore, what are the allowed values? That n minus 1. So 4 minus 1 is equal to 3. So therefore, the allowed values are 0, 1, 2, and 3. So is 4 an allowed value? The answer would be no. It's a forbidden value because the allowed values only for energy level 4 is 0, 1, 2, and 3. So this is actually incorrect. This is a forbidden value. Next, let's go. The third number here is the magnetic quantum number. Let's see if the magnetic quantum number is correct. Again, what are the allowed values for the magnetic quantum number? It's integers from negative L to positive L, including 0. So since the n is equal to 4, therefore the L is equal to 3. So if L is equal to 3, we know that the m's of L is equal to negative L to positive L. So that would be negative 3, negative 2, negative 1, 0, positive 1, positive 2, and positive 3. So hence, m's of L, which is equal to negative 2, is an allowed value. Why? Here, it's negative 2. So negative 2 is an allowed value. Next is the last number here is the magnetic spin quantum number. So the allowed values are positive 1/2 and negative 1/2. So here is negative 1/2. Is it an allowed value? Yes, correct. It is an allowed value. Now, after that, you're going to assess the overall results. If even there's only one rule that is violated, then the set of 4 quantum number is forbidden. So this would be all incorrect. So is this set of quantum numbers forbidden or allowed? The answer would be yes, correct, forbidden. Why? Because it violated the rule for the azimuthal quantum number, because the allowed value for the azimuthal is only from 3 to 1, 0. Okay, did you get the hang of it? So let's have another example. Refer to the set of quantum numbers 2, 0, 0, positive 1/2. Now let's see if the set of quantum numbers are allowed or forbidden. So let's start with 2, the first number. So this is the principal quantum number. Now, how are you going to answer this? Fill in the blanks. Okay, can you please read it? What do you think is the answer? So principal quantum number, we know that in principal quantum number only integral values are allowed, which are positive integers. Hence, if n is equal to 2, is it allowed or forbidden? What do you think? It is allowed. Why? Because of course it's positive 2. Next, go to the second quantum number. This one is the azimuthal quantum number. Okay, so the allowed values are blank, hence blank is a or n blank value. So what are the allowed values whenever it's azimuthal? It's actually from 0 to n minus 1. So because the n is 2, that will be 2 minus 1, right? So 2 minus 1 would be equal to 1, because we need to include 0, that will be 0 or 1. So we got here 0. Is 0 a forbidden or allowed value? Correct, it is allowed value. Why? Because we can see here 0. Next, let's go to the third number, which is the magnetic quantum number. The allowed values are blank. The allowed values for is R blank, hence blank is a or n blank value. So what the allowed values for magnetic quantum number? It's from negative L to positive L. So the allowed values for is or are, because the n is 2, right? Therefore, the allowed values are -2, -1, 0, +1, +2. Hence, 0, is it an allowed or forbidden value? The answer is allowed. Why? Because you can see here 0. Okay, for the magnetic spin quantum number, it's +1/2. So we know that the allowed values are correct, +1/2 or -1/2. Because here, therefore, +1/2 is an allowed value. So therefore, the set of quantum numbers is allowed. Now, looking at this four quantum numbers, it describes an electron in the what orbital? Can you guess? Is it in s orbital, p orbital, d orbital, or f orbital? Take a look at the principal, azimuthal, magnetic, and spin quantum number. It is actually where? Or what orbital? It is actually S. Why S? Take a look. Take a look. It's 0. When you say it's 0, that means it is, the orbital designation is S. So with a spin of +1/2. So +1/2, what is the spin or the direction of electron? It is clockwise direction or spin. So is it forbidden or allowed? Okay. Okay. How about this one? 3, 4, -4, +1/2. Is this set of quantum numbers allowed or forbidden? So let's see. So let's start with the leftmost number, 3. We know that principal quantum allowed positive integers only. Hence, if n is equal to 3, is it allowed or forbidden? Correct. It is allowed. Azimuthal, let's go to 4. The allowed values, we know it is from 0 to n-1. So because the n is equal to 3, so that will be n-1 or 3. Substitute with n, that would be 3 minus 1. So 3 minus 1 is equal to 2. So therefore, the allowed values are 2, 1, and 0. So is 4 an allowed value? A permitted value? The answer would be forbidden. Why? Because it's only 2, 1, 0. 2, 1, 0 are the allowed values only. Let's go to the magnetic quantum number. So what are the allowed values here? So it's -4, the magnetic quantum number. We know that for the magnetic quantum is -L to +L. Because L is equal to -2, -1, 0, +1, +2. Why we started with -2? Because we know n-1, right? So 3 minus 1 is equal to 2. So therefore, the L is -2 to +2, including 0. Therefore, -4 is not a permitted value. Now let's go to the magnetic spin. Is it allowed? +1/2 or -1/2? So we see +1/2. So therefore, it is an allowed value. So therefore, is the set of quantum numbers permitted or forbidden? It is forbidden. Why? It violates the azimuthal and the magnetic quantum number. So how about this? List the following values of n, l, m sub l, and for the orbitals in the following subshell. 2p orbital. What's the value of n here? Okay, I'll give you time to think. What are the values for n, l, and m sub l under 2p orbital? Okay, it's the n would be equal to, okay, it's 2, principal energy level 2. L would be equal to 1 or 0. Why? Because it's n minus 1, right? So 2 minus 1 would be equal to 1. So therefore, the allowed values is 1 or 0. M sub L, it will be negative 1, 0, positive 1. How about 3s orbital? What are the allowed values? It's easy. Okay, so what's the answer? Okay, there we go. We have n would be equal to 3. Why? Because here it's 3. It's the principal energy level. So L would be equal to 210. Why is it that the L is equal to 210? Again, the allowed values for L would be n minus 1, including 0. Because n is equal to 3, 3 minus 1 is equal to 2. So that will be 210. So M sub L would be equal to positive L to negative L. Because L would be equal to 2, the highest number is 2, that would be negative 2, 0 to positive 2. So lastly, for the orbital. Can you do it on your end? Try. Okay, done. What's the answer for n, for L, and for M sub L? Okay, so n would be equal to 4. Why? Because principal quantum number 4. L would be 3210. Why? Because L is n minus 1. So 4 minus 1 is equal to 3. So that will be 321, including 0. M sub L would be positive L to negative L. So because the highest number is 3, that will be negative 3 to 0 to positive 3. Okay, so there we go. So in summary, there are 4 quantum numbers which dictate the shape of the orbital and the arrangement of the electrons. So first, principal quantum number, which is directly related to the distance of the electrons from the nucleus. Third is that azimuthal quantum number, which is the second one, is represented by letter L, which specifies the shape of the orbital. Magnetic quantum number tells us the number of ways the orbital can be oriented in space, or the positioning. And the magnetic spin quantum number would tell us the spin of the electrons. It could have a value of only negative 1/2 or positive 1/2. Okay, so what is the importance of this? In analogy, no two family of different, who have no affiliations would have the same address. My address would be different from your address. We may have the same street, we may be in the same subdivision, we may be in the same city, but we won't have the same address, right? So that is the same applies with electrons. So no two electrons can have the same set of 4 quantum numbers. So the 4 quantum numbers helps us to actually see the probability of finding that particular electrons in the atom using the 4 quantum numbers. So that's all. Thank you and have a great day.